Hello, everyone. My name is Krish Kalla. I am a rising junior at Phillips Exeter Academy in Exeter, New Hampshire, and today I'll be talking about a study I performed concerning how large language models distinguish human emotions through textual context under Mr. Priya Muzumudar at Polygence. So, to give you all a bit of background on the field, first we need to understand what natural language processing is. Natural language processing, or NLP for short, is the process in which large language models, or LLMs, process input text and return a desired output, whether that be a summary of a paragraph or an answer to a question. Many of you have probably seen large language models in action in the form of GPTs, specifically ChatGPT, the very popular generative AI that took the world by storm some years ago. In my case, what we're extracting is the sentiment or emotional tone of the sentence. This process of extracting the sentiment of a sentence is called sentiment analysis. Most commonly, this sentiment is in the form of a positive, negative, or neutral output. But models can be trained on separate datasets to output more specific emotions, such as happy, angry, or irritated. So, how does one perform sentiment analysis? Well, traditionally, the most common way was to use predetermined rules and annotated data to correlate sentences with each other based on similarity. These types of systems are called lexicon-based algorithms. Now, although this method is very straightforward and simple to implement, it has its drawbacks. Specifically, its inability to understand context and nuances within language. Take, for example, a double negative. If I have the sentence, I do not want to go to the store. Well, traditional lexicon-based algorithms would say, okay, I've got a not here and a not there. So I should make the sentence even more negative, even though you and I know that this is a double negative and actually translates to a positive sentence. This is the main drawback of such systems, which is why they are continuously being phased out in favor of more accurate and efficient algorithms. One such type is the machine learning-based algorithm. Such models now use statistical methods to classify text based on pre-labeled training data. These models use feature extraction techniques, such as part-of-speech tagging, where words are tagged with their part of speech and grammatical connotations associated with speech, and solve the features given to provide a sentiment. This solves the major drawback of double negatives in lexicon-based algorithms, but now presents a new problem. No temporal information is stored. Temporal information can have a big impact on a sentence's sentiment. One might say, I didn't like it then, but now I don't like it now. Although the machine learning-based algorithms will understand the double negative and make it positive, it won't realize that at the current moment, the speaker says they have a positive connotation of the item they are talking about, and negative and positives will ultimately cancel each other out, producing a neutral input. This is where deep learning-based algorithms come in. Such algorithms also classify text based on pre-labeled data and patterns, similar to machine learning-based algorithms. But instead of using statistical methods, use recurrent neural networks, which allow them to capture complex patterns in contextual information, especially the aforementioned temporal information within sentences. Such models are much more computationally intensive, but because of their accuracy and versatility, they have proved to be the standing winner amongst the three, which is also why I chose them in my work. So, now that we know what algorithm we're going to be using, what model will we choose to study? Well, going back to the background for a bit, let's look at the LSTM. The Long Short-Term Memory Model, or LSTM, is a type of recurrent neural network designed to capture long-term dependencies within sentences. It's particularly well suited for sentiment analysis because of its ability to remember important information over long sequences of text, while forgetting irrelevant data, addressing both the concerns for double negation and temporal differences. So, now that we know what model we're going to use, a model is nothing without being properly trained. The first step to this is to find a dataset. Datasets are crucial as they provide the backbone for what the model will be looking at while training. Since we aim to classify sentiments, we must look at a dataset that comprehensively manifests this, especially ones with real human-made sentences. Now, such can be found in many places, such as social media platforms, customer review sites, news articles, blogs, surveys, and questionnaires. In my case, I chose the second option, customer review sites, but rather than traditional e-commerce, I went with movie reviews, specifically those from IMDb. With over 50,000 movie reviews equally distributed between positive and negative, it gave the perfect dataset to train and test the LSTM. Next, we must pre-process the text from this dataset. This means removing any punctuation, special characters, and stop words, or irrelevant words that do not give any meaning to the sentence. This clean text is then tokenized, or converted into smaller units, which in my case are individual words, and special tokens are added throughout the sentence to ensure the input sentences all have the same length, to allow for efficiency when processing. Since we've already selected the LSTM as our model, we can move directly to the training and validation stage, where the LSTM's hyperparameters or initial configurations were chosen, and the process of feeding the dataset to each model began. Each sentence is fed to the model, and the model starts predicting whether it should be positive or negative. At first, it has no idea what it's supposed to do. It is effectively guessing, but over time, it slowly learns what the proper output for a sentence should be, and it keeps getting better. Now, this process can be fairly slow, continuously iterating for the entire dataset, especially if it's a large one. But throughout this process, the model's weights are tuned, slowly reducing the model's losses and increasing accuracy over time. So, how did the model do? Well, I initially trained it for 30 epochs, assuming the longer the model trains, the more accurate it would be. And while this looked true at first, with the model's loss stagnating at around 0.7 for the first few epochs, where it's still effectively guessing the outcome, it suddenly makes a dive down, reducing loss and increasing accuracy. But at around epoch 15, the model's accuracy made a sharp turn back down, and its loss started increasing, even though its training loss continues to decrease. This phenomenon is known as overfitting, and is the result of the model becoming too obsessed with the sentences rather than the parameters or patterns associated. This causes the model to tune its weights to suit the training data and only the training data, which causes the validation losses to increase because the validation accuracy will now decrease. Because of this, I concluded epoch 15 was the most suitable amount of epochs to train it for, which resulted in a final model accuracy of about 83%, with a validation loss of about 0.362. Now, although these numbers might not seem very convincing, and considering what's out there, yes, they aren't. But this is just the tip of the iceberg, and with significantly larger amounts of data, one could boost the model's performance. But what if we can see what's causing the model's accuracy to decrease so much? Above are two graphs, a bar graph showing the accuracies of each chunk or batch of sentences fed to the model during the validation process, and a confusion matrix, which shows how many false positives or negatives were captured by the model. And it's pretty evident where the model was failing. In the bar graph, the first 98 chunks are where the positive labeled sentences were being fed, and the accuracy for those is fairly high, somewhere around the 90% range. But from batch 99 onwards, when the negatively labeled sentences were fed, we can see a stark decrease in accuracy, with the average being about 75% and as low as 60. This is further apparent when we look at the confusion matrix, where the number of false positives is almost 3 times as much as the number of false negatives. To further examine this, I looked into the dataset to find what might be causing this and found 2 major causes. The first and most prevalent being sarcasm. Now, sarcasm is where us as humans assign a negative connotation to something that is otherwise positive and is majorly classified through tone of speech, but the model doesn't have access to such information. And when fed throughout the model, it will almost certainly classify it as positive sentences because of the way that it is written. There are no definite clues for the AI to pick up on this negative connotation, probing misclassification. The second is contextual nuances. Now, although deep learning-based algorithms are made to combat this, some may slip by, especially more contemporary references. One example is the phrase downing a bottle. Without any context, the AI has no idea what this means. But we do, as we've heard this multiple times, whether that be through media or society, and embedded this meaning in our head. So, now that we have trained and tested the LSTM, how do we understand what it uses to make its decisions? Well, since the model is trying to compare sentence similarities, what if we could map these on a 2D coordinate plane? To find out this relation, I used a t-distributed stochastic neighborhood embedding, or t-SNE for short. t-SNE is a method in which embedding matrices of each sentence are taken and mapped on a 2D space based on matrix similarity. This produced figure 4, in which the blue points are positive and orange points are negative. Now, this seemed odd at first, because it seemed that there was no distinction between the two, and they were greatly mixed, especially near the line x equals 0. However, there did seem to be a distinction between the 2 curved clusters. To further understand this, I mapped out those 2 clusters, producing figures 5, and connotated the blue cluster as cluster 1 and the green cluster as cluster 2. But I still didn't know why these clusters were happening. So I had to back out a little, back to the original sentences that constituted the clusters. This led to the creation of 4 word clouds. Now, a word cloud is a collection of words based on prevalence, where the larger words appear, the more prevalent they are in the actual data sets. Clouds A and B are from the blue and green clusters respectively, while clouds C and D are created from the initial positive and negative split. Feeding through the common words within clouds A and B, I couldn't find any defining factors that set the two apart, but C and D had some defining differences, with C having words like good and great displayed rather prominently, and D having negative words like bad, but also positive adjectives like good coupled in with negative words like not. This made me conclude that the aforementioned clusters don't have a proper distinction between the positive and negative sentences, and aren't a result of sentiment. Only the initial relative positioning can be considered, and while this may seem counterintuitive at first, especially with the negative ones, we must remember that sarcasm and negation were common occurrences within the dataset, which effectively causes the two groups to have relatively similar words with drastically different meanings. Effectively, this means that the LSTMs connect the initial connotation of a pattern within the sentence and compare that to those found in other sentences to make their predictions. And the similarity of the actual sentences do not make a difference in how they are classified. And because of this, it makes the LSTM's applications limitless, as it does not need to be fully confined by sentence similarities, which were a major part of the other two types of algorithms discussed earlier. This means deeper insights into emotional standpoints and, if the problem of sarcasm is solved, more accurate classifications across the board. Thank you very much for listening to my presentation, and I hope my study was interesting to you all.